Hey everyone, Mr. Skelton here, back at it for lesson 2 in unit 6, and today we're going to be talking about bisectors in triangles. And this is really a review. We've talked about both of the type of bisectors, angle bisectors and segment bisectors before, so hopefully some of this you'll find to be relatively painless as we go through it. Okay? So the first thing we're going to do is talk about the perpendicular bisector, what a perpendicular bisector is. And then the second thing we're going to focus on is the angle bisector. So those are the two big keys today. It's really knowing what those two are, what they look like, and how we can apply them to problems. So let's take a look. A perpendicular bisector is a two-part definition, right? Perpendicular means that two lines intersect at a 90-degree angle. A bisector, remember we always talk about a bisector means to cut in half, right? To bisect, bi means two. Cut in half perfectly. A bisector is a line, could be a segment, could be a line or a ray that cuts a segment in half. So this is important. A perpendicular bisector is any segment, line, or ray that cuts a segment in half and meets at a 90-degree angle. A lot of the times we look at something like this. I'll just give you a rough sketch. Okay. I'll call that point A, I'll call that point B, C, and D. Right? We've talked about this. AB, I always say, who's doing the cutting, what's getting cut in half? AB is the perpendicular bisector. What's getting cut in half? CD. So we would say AB is the perpendicular bisector of CD. CD is getting cut in half by the markings here, and when it gets cut in half, it's meeting at a 90-degree angle. All right? That's a perpendicular bisector. Number two, an angle bisector. Again, angle bisector is a segment, line, or ray that cuts an angle in half. So something that would look like this. If I drew an angle, I'll call it T, U, and V, okay? And I put most of the time we see them as rays, and I call this in point A. We have these markings here, those little swoops. That means UA is a ray. UA is an angle bisector, and you know that because this angle of TUV is getting cut in half. So that's what an angle bisector looks like. Again, that should be review for us. Most of you know that. So there's a theorem that goes along. We're going to kind of break these into two. We're going to talk about the perpendicular bisector theorem first, and then we'll talk about the angle bisector second. All right? So this is kind of a little challenging to think about. Hopefully we'll get through it. If a point is on the perpendicular bisector of a segment, then that point is equal distance from the endpoints of the segment. Holy cow. Okay, so let's look at this example. This is a proof. I'm actually not going to make the proof, but I'll just kind of go through it. It says given CD is the perpendicular bisector of AB. CD is cutting, I always think of it this way, CD is cutting AB in half and is perpendicular. So that's what that means. All right. Now it says prove that CA is equal to CB. That's what this perpendicular bisector theorem says. Okay. Well, if we use the reflexive property, we know CD is equal to CD, and I know this triangle is now congruent to this triangle by what? See if you can remember. HL theorem, right? Good old HL. If we were making a proof here, that's the HL theorem. So why is CA congruent to CB? CP, CT, C. You're probably having flashbacks right now of all our proofs. You're thinking, no. Okay? But this is a proof of this theorem. So if these sides are congruent to each other because point C is on the perpendicular bisector, if I picked a point, if I just drew another triangle, I know that's a terrible looking triangle, but if I drew another triangle and put a point here, and I drew it to the end points, those two would be the same distance. Any point that's on here, if I put another point here and drew them to the end points all the way out here, I could put 3 tick marks there. Any point that is on the perpendicular bisector is equal distance to the sides, because this distance, if I put 7 and 7, those distances are the same. You have congruent triangles every single time. Okay? Now, sometimes this is kind of hard to apply, so let's take a look at this picture. It says, which segment is the one getting cut in half? So if you look at this, what segment is being cut in half? Well, just look at the markings here and here. So that means CD is getting cut in half. Okay? Which segment is the perpendicular bisector? In my mind, I read that as which segment is cutting in half CD? That would be AB. AB is cutting in half CD. Now, it says, what is CA, segment CA, equal to? So I kind of flip this around, okay, to make it look like the theorem. So here's my congruent tick marks here. They want to know what CA is equal to. Well, if my 90-degree box is here as well, and these are equal, okay, this is the reflexive property, just like what we talked about, then CA is going to be equal to AD because of CP/CTC. So CA is congruent to CD. Now it says BD. What is BD equal to? Well, again, if you look at the picture like this, okay, here's BD, here's your 90-degree box, right? You could say the reflexive property here, and you have HL and HL, so BD would be equal to CB. That can be a little confusing at times for students. It just gets a little tricky, and I can show you an example here in a second of how that works. So let's look at the back here. This is the converse of the perpendicular bisector theorem. It says if a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector of the segment. So it says find the value of x, explain how you got it. Well, if I know that these distances are both 9, that means that those distances are the same, which means F has to be the perpendicular bisector of HG. So I know that 5x minus 3 and x plus 5 are equal to each other, so I just set them equal to each other and solve. Okay? 4x equals 8, and x would equal 2. And I kind of just explained it, but if you want to write that in words, you can. The biggest thing is saying that these are 9, so you know they're equal distance from the sides, so that these have to be congruent, thus perpendicular bisector. Okay? Angle bisector. So this is the second type of bisector we're going to talk about here. If a point is very similar to what we just talked about. If a point is on the bisector of an angle, then that point is equal distant, has an equal distance to the sides of the angle. Okay. So it says name the angle bisector. We'll just look at the markings. Here's your little swoop, there's your little swoop. So CF is cutting this big angle of ACE in half. Okay? How do we know it's the angle bisector? I'll just say the markings. Right? These little markings right here and right here tell you that that angle of ACE is getting cut in half. Since F, which is right here, since F is on the bisector of CF, then F is equidistant to the sides. So BF and DF. And just think about this for a second. An angle bisector, which is CF, cuts this angle in half. So anything that's on it, if it's completely cut in half, should be the same distance to the sides. That should just make sense because CF is right in the middle. If something's getting cut in half perfectly, then anything on this bisector should be equal distance to the sides because this is going right down the middle. Okay? So which symbols are necessary in order to say that FB is equal to FD? I just marked them down there. I put my tick marks there. And then it says find x. Well, I know that 5x has to be equal to 2x plus 24. So I get 3x equals 24, so x would equal 8. And then it says find the actual measure of FD. So I'd plug 8 back in here. So 2 times 8 is 16. 16 plus 24 should be 40. Okay. Moving on to the last part of this, which is the converse of what we just talked about up top. So it's the same type of problem. It says if a point on the bisector of the angle is equidistant from the sides of an angle, then the point is on the angle bisector. Okay? So this is just the same thing as that we just did here, just kind of going backwards. Right? So this one says, how far is K from ED? What is the distance from K? Here's K, and here's ED. What is this distance is basically what they're asking you. Well, this has 2 markings, this has 2 markings, and then there's a 10 here. So that means this has to be 10. So K is 10 units away. Since K is equidistant from the sides, which DE and HE, right? K is in the middle always because K is right down the middle on the angle bisector. Because these are equal distance from each other, then we know that K is on the angle bisector of angle DEH. Okay? K is right down the middle. So if this is 10, this is 10. So it says to find X. Well, since we know K is in the middle, we know that these angles have to be congruent. So it's 2x equals x plus 20. And I would just get x equals 20. I would subtract x over, so I just get 20. Then it says find the measure of DEH. DEH is the entire thing. Well, if x is 20, 2 times 20 is 40. So if that's 40, you know the other angle is 40, and they want DEH. They want the whole angle here, so 40 and 40 makes 80. Okay? Last thing I want to do is I want to go back to this problem here, because this is a problem you'll see like on a quiz or a test, and I don't have an example, but I'm going to show you one here. I'm going to go back and kind of redraw this picture almost right next to it so you can kind of see. And I'm going to give you an example that really trips students up a lot. Okay? And I'm going to draw almost the same exact picture, except I'm going to put some numbers in here and see if you can figure this out. Okay? Let's see. I want to put an 8 there, and I want to put, let's see. So this is a problem you'll see on a quiz, and it says, or a test or a homework, and I'll say, very simply, I'll say, find the value of x and find the value of y. And what a lot of kids are going to do is they're going to get this a little, they're going to get confused a little bit here, okay? So I like to look at it like this. If I turn it sideways, and I always keep my perpendicular bisector here, I know because of the reflexive property that those are equal to each other. This is equal to each other in the middle, right? If I'm kind of ignoring, if I'm ignoring this bottom part here and just looking at it like that, these two triangles are congruent by HL. So this and 8 would have to be equal to each other by CP/CTC. So that would be 8, right? And if I flip this around, oops, I'm getting a picture here. And if I flip this around and try to ignore that bottom part, right? And if this is 90, that means this is 90, okay? Here's your congruent parts here and here. This would be the reflexive property. So these two would be equal by CP/CTC, so that would be 7. I'll have a lot of kids on a quiz or a test look at this problem and say, oh, that's 8, that means that is 8. This is 7, so this is 7, and they get that wrong. So what I always try to do is tell kids to really focus on where are the congruent segments, where's the perpendicular bisector, what's getting cut in half, and find your HL theorem triangles, and then just use CP/CTC, like we did right over here, to determine what is actually equal. Because this problem right here, I guarantee you'll see it, it'll confuse kids, and I'll have a lot of kids put 8 and 8 and 7 and 7 and get that mark wrong. Okay? So if you got some questions, make sure you ask in class. We'll talk to you soon.